images would be the mean value. So you can have the mean value of the gray, which means RGB together, like a combined mean value. Or you can have the mean values of red spectrum, green spectrum, blue spectrum. Or you can convert RGB into a hue, saturation, intensity framework. And I think next slide shows that how to convert that. And if you convert it to the HSI values, you can have the mean hue, mean saturation, and mean intensity values. You can also, so in this case, the mean values are used as features. You can also calculate the deviation for all of them. So the standard deviation then becomes the feature. You can calculate the mode, which is the dominant the gray value. You can calculate the median, which divides basically in half. You can calculate energy or zero order spatial movements, and which is basically sum of gray levels of particles, basically. So yes, you are summing all of the F values. So not the coordinate values, but of the gray level values. That will give you the energy, which is also referred to as zero order spatial moment or energy of the image, and that energy becomes a feature. Okay. So when we are dealing with the color, I keep mentioning that red, green, and blue are the three main colors. So if you imagine a parallel packet, the black is at the origin, and the white would be out the corner, which would be opposite to that, would be the corner which would represent the color white. Red, green, and blue represent an X, Y, and Z, and the other corners represent the magenta, cyan, or yellow color. And sometimes people would also say that they are using MCY as a framework for color imaging, but MCY are not primary colors. So you're always using RGB, but you can convert RGB into MC and Y framework if you need, but there's no reason for. So typically you would convert with RG from RGB to HSI, or sometimes because the food industry uses the Hunter Lab colorimeter for measuring the colors, and then in this case use LAB. So you can also convert RGB into LAB, or you can convert LAB values into RGB. And typically, especially if you were going to design an imaging system or machine-based system for measuring the color of the food, and most people are familiar with the LAB, so you take the camera, take pictures in RG, and then you can convert that into LAB. Okay. Any questions? No. So this is the basically how you convert the RGB to HSI. So if blue value or blue color is less than green color, then basically H is equal to theta, and if it is more than green color, then H is 360 minus theta. So that's how you would get the hue values from the RGB. And then theta is basically calculated from RGB values, which is the inverse of that function. And from once you know the theta, then you basically can substitute the above equations, and you would know the value of H and the value of for both situations, whether blue is less than equal to green or greater than green. And then S is calculated from RGB by using the equation in the middle, minimum of RGB. So you take minimum of red, green, or blue, whichever is the lowest in the three colors, and then divide that by summation of three colors and 3 over that, and then subtract that from 1. And I is basically 1/3 of all three colors together. So because that's really referring is intensity. So you take the intensity would be 1/3 of the three colors together. Okay, so that's how you can convert the RGB to HSI. And as I mentioned, you can also convert to LAB model. You can also convert to CMY, but there's no region for using those color spectrum. So color features, as you can see, are very simple to calculate, because all you are dealing with is you're calculating the mean, mode, median of either the red spectrum, blue spectrum, or green spectrum, or the combined gray spectrum. So the calculation of color value, as you can imagine, would be, but you are doing this for all pixels. So it's when you are writing a small computer program, you basically would take the intensity values, you can sum them, you can calculate the mean. So it's very simple to extract the color features. Or writing the algorithm for extracting color features is very straightforward. But whether you saw in the morphological features, there were a lot more calculations and equations involved, but in color, there's not that many features you can extract. Then the question arises that once you have the color features, why we need more features, or why is the textural features needed? And this image is a very good example. Like if you look at this image and you count the amount of red, amount of green, and amount of blue in both pictures is identical. So if you did the color values, whether you calculate the mean, it would give you the same number for both images, for RGB or for grayscale, median, mode, everything would be identical. So these are two, but they are two different images. Like if you look at the two images, visually you can tell that they are different. Okay? But if you were using, and this is example tells you that if you were using color features, you would get basically you would get these objects are identical. Okay? But the difference is how the color is distributed in the image, and that distribution of the color or distribution of the gray values is what you basically utilize to calculate the textural features. So the textural feature is nothing but trying to understand how is that color distributed in the image. So you would look at the distribution, and the features then extract from the property of the distribution of the color are referred to as textural features. And why we need the textural features are, the texture is a surface property. So when you look at any object, you look at the object, you would say it is rough, it is fine or smooth, it has granulations, it is like the granulation is regular or has a pattern, patterned granulation. So that information you are trying to extract, and that information usually you can get from the textual features. And that helps improve the classifications, because as I said, the color features might be similar. It could be also the situation where kernel of wheat and barley, for example, may have similar morphological feature if the barley tip got broken in the handling process. And then, but if you look at their surface, wheat has a much smoother surface, as all of you would know, and barley has a much rough surface. So textural feature might help in distinguishing between wheat and barley in that case. Okay, and there is maybe some morphological features, some color features, because between wheat and barley the color is also different. So that would also help in classification. Okay, so that's what the texture is. Basically, it is a surface property which describes the visual patterns on the surface of the object, and critical information on the structural arrangement of that surface, which deals with the coarseness, smoothness, fineness, granulation, regularity. And there are three different approaches used for extracting textural features: a statistical approach, the structural approach, and a spectral approach. Okay? Is that clear? This previous image, you agree that they're identical in color? Amount of red is equal in both images, amount of green is equal, amount of blue is equal. Okay, and if they're equal, then you would get exactly same features from both images. Okay? So the statistical method of extracting textural features, it's basically the structural, or when you use the statistical tools, you would basically be extracting features which would be help characterize is the smoothness, graininess, and coarseness on the surface. The simplest method is to take into consideration of the moments of gray level histograms, and then from those moments you basically calculate these textual features. So the average intensity you can calculate basically by using this equation, but the problem is that if you just use the moments, then you run into the problem of that you still don't get all of the value, or you can get, or all of the characteristics you can get from the surface. So you use the gray coherence matrix and the run length matrix. So this one is just you calculate the average intensity for the image, where in this case Zi are gray level of the image. So they are going from 1 to G, or whatever that upper limit would be for any image. And the PZ is the probability density function for that particular gray level. So the nth order moment of the gray level histogram basically then can be calculated from this simple equation. So though that's the order, the moments is the one of the features you can access textually. So the 0 and first order moments, which means mu0 or mu1, are 1 and 0 respectively for all objects. So it doesn't matter what object you're dealing with, so they really don't provide you much information in that sense, because of the, if they're same, they're not going to have the classification. The second moment, mu2, is called as variance, and it describes the relative smoothness or the distribution pattern of gray level intensities. So if you calculate using that function, the previous equation, mu2, that would give you basically the smoothness or distribution pattern of the gray level. The smoothness would characterize. The third order moment, mu3, is called skewness, and that describes the symmetry of the histogram curve above the mean gray level. So basically it gives you the symmetrical nature, and the symmetrical nature would tell you in how the surface characteristics of the scales or granulation is patterned. And fourth order moment is called kurtosis, and that represents the degree of peakness or flatness of the histogram of the object. So that would give you undulations and peaks and valley basically. So that would give you more appreciation of the roughness of the surface. Okay. So in addition to the moments, the most commonly the approach are two approaches. One is the gray level co-occurrence matrix, and other one is referred to as gray level unlength matrix. So we'll go through those two now. So in the gray level co-occurrence matrix, it is a two-dimensional matrix in which two pixels separated by certain vector occur in an image, and that vector can be varied. So what you are looking at is for example, like gray level 1, and is it separated from gray level 3 or gray level 6, and how are they separated? So you are trying to understand that separation. So in the image, if you have a lot of undulations, you would have a gray levels would be varying quite up and down. So when you look at just the surface of the gray levels, and the roughness basically dictate maybe use the numbers. For example, if you have gray level is 100, the next pixel could be 110, next pixel could be surrounding pixel could be 120, then you might go down to 90. So you can start seeing almost like those peaks and valleys on the image that you are trying to capture from that. And what you are looking at is how those relations. So the gray level of 100, are they distributed uniformly in the image, or are they distributed in a certain corner, or distributed on one side, one corner, and another corner, but not in the middle? That gives you the information which can be used for classification. So GLCM provides the probability of a particular gray value pixel that occurs at a specified direction. So you always use the changes in the gray level, are they occurring in the horizontal direction, or they are occurring in the vertical direction, or in the diagonal directions. So you always try to understand those distributions along 4 different directions, and then once you understand in 4 different directions, you can combine them and then develop the features for extracting the textual features. So some of the terms, energy I already mentioned, but the contrast is the term which is made of the contrast of the intensity between a pixel and its neighboring pixel, or local variation in the image. Basically, that's what you're looking at. Okay, so that's what the contrast would be, because you are looking at the variations in the pixels. Energy is the term, and also it is also referred to as uniformity. So energy also termed as uniformity, and when an image is more homogeneous, then the value of energy is larger. And energy equals 1, it is a constant. It is a constant image. That means there is no variation in the image. You basically have a flat surface or a smooth surface, and also termed as the same term is also referred to as the angular second moment. Variance, on the other hand, is a measure of how spread out are the gray level distribution, that the statistical term is trying to then show how the gray levels distributed. And the cluster prominence are skewness features of the matrix, i.e. the system lacks the symmetry. So that information you use for calculating. How you calculate these, and then the further term defined on this side is the correlation, which then is the measure of how much correlation exists between pixel and its neighbors. So correlation could be like if you have a pattern. So like for example, the one pixel could be 100, surrounding pixels are, let's say, 110. Then the next you have a similar pattern, 100 and surrounding pixel 110. You are seeing there is a pattern on the surface. Okay, like we're almost looking at a carpet or something, and you can see the pattern, and that would reflect then in your intensity values or wave values. But you are then trying to see that correlation, and then from that you would then predict the pattern. So how is the measure of how much correlation exists between an individual pixel and its neighbor over the whole image? So whether it's linearly dependent, or intensity is changing linearly, or it is changing in a parabolic way or quadratic way, that information would be useful in classification. Entropy, it represents the randomness of intensity, so how randomly intensity is distributed, and with the and frequent occurrences of a specific color configuration results in higher value of entropy. So if you have a patterned object, entropy value would be high. Inverse difference moment provides the information about the smoothness of the image, like homogeneity, and have a higher value if gray values of the pixel pairs are similar. And homogeneity determines the similarity of the pixels, or local homogeneity of the pixel pair, which is the uniformity in the image. So how we calculate these is you first create from your image, again keeping in mind the image is basically the matrix, like we talked about two-dimensional matrix, for color, basically you can almost imagine as if there are three different matrices, one for red, one for green, and one for blue. So from that gray level, that matrix, which is your original image matrix, from that you want to calculate first is the gray level co-occurrence matrix, and once you calculate GLCM, then you calculate the features from that. So the co-occurrence matrix, the elements of the co-occurrence matrix Ij are calculated, calculates the co-occurrence of the pixel with gray level I and j at distance d. So how far they are. If you're looking at the gray level, maybe say 100, and gray level 110, and you can pick the distance. The distance will be 10 pixels or 20 pixels, and they does it occur in that sequence, and how many times it occurs in that sequence. And then you do that in the horizontal direction, you do that in the vertical direction, as well as on 145 diagonals, 45 and 135 degrees. So in 4 directions you do that assessment of how these pixels are distributed. Using that, then you calculate the GLCM. So this example, I don't know if you can read that this part. So the example is again the A is basically showing you the directions. So this one is not. This is an example of the A basically, which is a 4x4 image. Okay, so the image basically have 16 pixels total, and where the real image, as I said, would be 640 by 480. So you can imagine the number of pixels you have. By using this 4x4 matrix, you can appreciate or that how the gray level is calculated, and then you basically in a program you would do the same computer program. You assign that the size of the image, then wouldn't matter because computer will do the calculation. So using 4x4 image as an example, you can start appreciating how the gray level co-occurrence matrix is calculated. So at 0 degree, in this particular case, you are looking at is the first column, or you are looking at the distribution of gray levels. In this case, gray level values are 0, 1. As you can see, the image only have gray level going from 0 to 3. So the maximum, gray level value, there are only 4 gray level values, 0, 1, 2, and 3. So they would be going on the, so you are a horizontal direction, and what you're looking at on the direction going on the row direction, what you're trying to find is that how the gray level of 0 is connected with 1, how many times if you go in the horizontal direction. So when you start counting, so like if you look at the on horizontally, you would see if you go in the from left to right, 1 is connected to 0 in first row, it's connected in the second row, but it's not connected in third. So it's connected basically twice, but then when you go from left to right, 0 connected to 1, so that's where the 4 comes on. Okay. So if you do the same there, so is it all you're doing is going horizontally and then trying to see 1 and 0 how close they are, or how many times they occur together. Okay. So you would say why do both ways? The reason is because in normalization, if you don't, you can do halfway, but then the normalization coefficient would be basically half. Okay. And for a computer program, once you write the program, it's easier to do that calculation. So next would be same thing, 0, and is it connected to 2 anywhere? So if you look at how many times it's connected, 0, 2, it will be twice. Because when you're going in the horizontal direction, first of all, there's nothing between 0 and 2. Second has nothing. Third has 0 and 2. And fourth has nothing. So 0 and 2. And then if you go back to 0, that's where 2 comes from, this number here. Okay. So 4, 0, 1. This is 0, 2. Similarly 0, 3. Any connections between 0, 3? So why I put number 1 there?
0, 0, 0, 1, 0, 2, 0, 3. It starts like 0, 0.
Yeah, no, but we are going in the horizontal.
Yeah, the first one is like 0, 0. This is 0, 0, 0, 1, 0, 2, 0, 3.
Oh, 0, 3. Yeah. Okay. Okay. Is that clear? What tell us all?
So 0, like when we are going horizontally, how many times 0 and 0 occurs? So here you go here like 1, then 2, 3, 4. So 4 times 0 and 0 occurs. So that's how the 4 comes here. But this next one, like if you look here, 0 and 1. So how many times 0 and 1 comes together? So that's like, if you go this way, 1 and 2. So 2 times. So and the next one will be 0 and 2. So anywhere 0 and 2 occurs like 0, 2, and rest of the time no, that's why it's 1. And 0 and 3, if you look anywhere 0 and 3 connected, nowhere, that's why it's 0. So that's all, the second one will be 1 and 0. So they count how many times the connection occurs.
And you would do the same in vertical directions, you would going along the columns. And the same things we look at in the, so the 90 degree angle, and you are now looking at the same, so 0, 0, 0, how many times it connects when you are going in vertical direction? Yeah. 4 times. So that's why the number 4 is in the, for 90. Similarly, you can look at the 45 degree angle, and then when you are doing 45, you would be going, it's too bad, there is no pointer here, eh? No. So when you are 45, I'm not also I will use here. So when you are going 45, your angle would be going basically, so assuming this is not there, like this part and this part is not there, so you are going basically this, would be 45 degree angle. So this, you will be looking along this path here, then this path, and then this diagonal here, and this path, this path. When you calculate a 45 degree angle, this is how you would be looking. Under 35, you would be looking basically here. So in this case, you would also no connection because nothing in that line. Connection would start here, depending on what gray levels are there. So between 1 and 1, but you're going along this direction, and then this. So that would be 35. So you basically create a the co-occurrence matrix at 0 degree, at 45 degree, 90 degree, and 35. And you add these together. So 4, 2, 2, and 4. That's where that 12 is coming from. So you add those basically 4 directions together. You get the rate level matrix. Divide that by the constant, normalization constant, which is calculated by this equation. The normalization constant, which basically is based on the number of object pixels in the horizontal direction, and ny is the number of object pixels in the vertical direction. So you take nx and ny, from that you can calculate the normalizing constant, so very easy to calculate. And you divide then every pixel value in the GLCM by this k, and that gives you the elements of the CM matrix, or the co-occurrence matrix. Okay? So once you have these elements, which means like in this example you would have 16 of these elements, 4 by 4, and using those then you can calculate. So gave you the definition before, and now it's a method of calculating. So we want to calculate the mean, then you basically take those elements and then you sum them, and then calculate what the mean value would be, which I already normalize it, the matrix by divided by k. Similarly, you calculate variance, you can calculate the uniformity, and ng is the maximum gray level of the image. Similarly, you can calculate entropy. But once you have calculated the co-occurrence matrix, calculating these features is very easy. They are simple summations, mathematically very easy to write the equation. Maximum probability, you calculate from that, and inertia you can calculate by using the elements of the matrix. Okay. Similarly, you can calculate correlation, homogeneity, and cluster, which we defined earlier about cluster image, but this is how you would calculate that. Okay. Any question? I think then we go to the document. Any question on the GLCM? No? Now, run length. Run length for RM, run length matrix is a representation of the occurrence of the collinear and consecutive pixels of the same or similar gray values. What you're looking at is, like for example, if it was a gray level 100, and does it 100, 100, there are 4 in a row, or 4, or is it 5 long, or is it 6 long? So you're trying to find out is that how often the gray level is constant. And there could be only, if there is no pattern, then it may be random, and there will be no run length might not be at all present in the object. When it is a pattern object, like I think the surface of the, if you look at the Barley kernel, if you look at the Barley kernel is a longer axis or near axis, you would see the lines. So when you would take image of a Barley kernel, you start seeing those longer run length. So we are basically looking at that how many pieces of those equal gray level occur in the image. Once you calculate those, so the matrix element of RMIJ is the number of occurrence of gray level I with the run length j. So that means saying, say gray level 100, and run length is looking at how many pixel long it is. Is it 5 pixel long, or is it 10 pixel long? And you're counting, basically your computer is counting how many of those are occurring. And then you do the same in 4 directions. It's 0, 90, 45, and 135 degree. And once you have done that, you basically then add them together. And the row of the gray run length matrix is the gray levels, and the column is the run length. So you would have the run length is given in the row, and whereas the column basically gives you the run length. So from there, this is the example of calculating the GRLM, or gray level run length matrix, again for the 4 by 4. So for example, if you go back, you're saying that the row is the index of the gray level, and row index of the gray level run length matrix is the gray levels. So you are going basically 0, 1, 2, 3, and then on in the horizontal direction, or in the columns, you are putting is the run length. So in that means, what that means is, so in this particular case, what you're looking at the gray level, for example, 0. So here is the gray level 0, and here is that 0 occurs side by side how many times. Okay, so one run length, there is basically 0 itself. 2 would be that there are 2 together. 3 would mean there are 3 zeros together, and 4 would mean there are 4 zeros together. And that's what you are basically looking at. So in that case, if you calculate, so for 0, when you're going in the horizontal direction, how many times you would see in the 0, looking at the image at the top, you would see once only. Going in the horizontal direction, how many times you see 0 once? So you only see once. In the row 3rd, there is a 0 by itself. So that's where that 1 is coming from. Okay. Similarly, when you're looking at zeros but 2 together. So how many times that's occurring? You will see that occurring twice. Okay, in the horizontal direction when you're looking at. And then 3 zeros not occurring, 4 zeros not occurring. Similarly, if you go to the grade level 1, how many times ones by on their own? 0 times. So that's why you have a 0 in this matrix here. You have a 0, and ones together occurring twice, and that's why you have 2. So you can basically, and then going same thing in the horizontal direction, you calculate, you do the same in the vertical direction, same in the 45 and 135, and that's why you get the 0 degree RM, 45 degree RM, 90 degree RM, and 135 degree RM. You add them together, and this basically becomes your elements of your run length matrix. So this is the information then you use for calculating GRLM features, and those features then are basically these features. So run length R, which is calculated by basically the summation of those elements. Short run is calculated by the equation given there. Similarly, long run is calculated by the equation. These are the shortest pair together or long pairs together. That becomes then the feature in your classification. Gray level non-uniformity is calculated by the equation given there. And then run percent is another feature which is calculated from those elements. Once you have calculated those elements, entropy is calculated by using that equation, and run length non-uniformity calculated by using that equation. So you can calculate basically, once you have calculated the run length matrix, from that you can calculate these features, and these features then are used for classification. Okay, any question on the GLCM or run length matrices? Okay. The calculations are very simple once you write the program. The concept basically is that you are trying to look together is how these gray levels are distributed on the surface. And these features basically help you understand that, and that is what is characterizing. So the image which we saw earlier, so these basically will help you characterize this variation here, because it would start seeing the patterns is different on that image than what you see on the left hand side. And using that information, you would be able to characterize that it is and what this picture is coming from. You would say this is different than that picture, and with with color alone, you won't be able to characterize. Clear? So another approach, now I would say, if you start reading the papers in the literature, you would see majority of the features extracted for textual analysis come from GRLM or GLCM. So even the moments are very rarely used. You can use them. Or the textual features could be extracted from the structural side, where the structural approach deals with the arrangement of the image primitives, decide the activity on the methodologically space parallel lines. So you, in this particular case, you basically are comparing is that if you had almost like overlaying a rod on top of the surface and see how it matches with the as you move along the surface, and the rod could be of a certain pixel length or whatever pattern you choose. Like you can choose a square pattern, and then you are moving that and comparing that, basically that does it fit over as you move along. So then you basically come up with the pattern. So that's what the structural features are extracted. And the spectrum basically I put this color text on based on Fourier spectrum. So you take Fourier spectrum of the properties of the image surface, and are used to identify global periodicity in image by determining high energy and narrow peaks in the spectrum. Okay, so both spectral very rarely used, but certainly they could be used if you want to extract them. With GLCM and GRLM, extract most of the textual feature or most of the information on the surface of the object, which you can use for classification. Okay, so the next basically step is, so if you write your own program, and as you know, if you write a program and if you make a mistake, an error in your write of the program, now the error could be two types. One is that program doesn't even execute, so that error is fixed by debugging the program. But you can also make error where it's calculating the area and you have multiplied by a wrong constant. So it will still execute, but may give you area double than what actual area is, or that, and same thing can be true for any feature. So it could be the perimeter is the same thing where you have put a wrong constant multiplier somewhere or double division. You can't test that error by debugging the program. So the one thing you want to do is that you want to do is so if you write your own program to extract that features, you want to validate that your features you are extracting or your algorithm you have developed is giving you the accurate values. So you can make some simple images. So like this is an example. Example is you can make an example circle, ellipse, and because these are analytically you can calculate their areas, you can calculate parameters. So if your program gives you the same value, then you know the program is working. So that it gives you the comparable results, and you can do that in terms of pixels or in terms of the physical dimensions. So you can use, so these are the kind of images, you can generate images in Image Pro software or Image Shop software, or I think even MATLAB has a capability to generate artificial images. And again, you don't have to use these, you can use any images, but use some smooth, nice images for which you can calculate the parameters by hand, and then you can verify that your program is giving those values. Okay? So these are the images. So for example, when we developed our algorithm which extracts about 236 features, these are the images we used for testing of the morphological features. Okay, and then see that is correct. There's another way of testing your algorithm is that use the existing software. So for example, your own algorithm or your own computer program calculates the features, but you can use the MATLAB program and using the same image, feed it to the MATLAB and feed it to your algorithm, and if they give both give the same number, like within a region, like area would be 200 pixels by one and 205 pixels by another, they would be considered comparable. But if one was giving 200, one is giving 300, that's a pitch error, and would say there's error. Now you can say that hopefully there is no error in the MATLAB. So you would say that there is probably error in my program. MATLAB has been tested quite. But if you ask somebody else's algorithm, then it's possible in their algorithm there is an error. So you want to use a reliable program to test your own algorithm. So these are the images we use for testing of the morphological features. But you can generate any images basically. These are the images which we used because these ones, again, these are very oblong shapes, so you would see the distinct between the major and minor axis, for example. So just for testing of the major and minor axis, use these images, and again you can use that in MATLAB or compare with the output from MATLAB and your own software. These were used for testing of the color features because of the intensity, and especially the image on the left. It is showing that variation in the color, and it should show up then in your results from your algorithm, that variation. And these are the values we use for testing of the shape moment, because you should get because a circle and a square and rectangle have well-defined shape moments, so your output should give you the similar numbers. And these were the images used for testing of the textural features. Okay, so and then you should get comparable results between your software and the other software. Okay, I think that's the next slide. Okay, so any questions so far? No?
GLCM or GLRM give same returns or
No, because one is, I think one is looking at how the closeness of the gray levels are distributed on the surface. Other one is looking at, is there a pattern? Is there a pattern in that distribution? So run length, the best way to look at it is for example, how long the same pixel occurs together. How many? So like for example, if you have 100 and it does 5 much together, and if that repeats, that means that 100 gray level is occurring uniformly throughout the image. Okay, so that's what the run length is giving you, the appreciation of the pattern of that. Whereas in co-occurrence matrix, you are looking at the closeness of those gray levels.
So for every analysis, it is mandatory to perform both, or we can either select anyone?
Oh, you can just do the features based on run length, or you can do with the co-occurrence matrix, or none. It would depend on the application. That if you are interested in understanding, like if you think the color features are enough to do the characterization. So to give you an example, like if you were characterizing, let's say green peas, and you were looking at the mold damage on the green peas, which would then go to a gray color or black color. So in that case, basically taking a green filter or green image is basically green color, not in RGB, just with one filter or in green spectrum, you'll be able to see very quickly just by mean value that this is a P and this is not a P, this is the damage P. Similarly, if there was a stone that would be very different, it was a gram kernel with the P's, it would be again very different colors. So in that case, only feature you need to extract is the mean value of with the feature. You don't need any other features. Like all the features we talk about, you don't need any of them. And just by using that mean value, you can characterize which is a P's and which is a P kernel and which is not a P kernel, and then design your machine to basically either use the air jet and then throw out the non-P kernels. The liquid samples, I would say typically the bioimaging is not done because usually you are looking at either the absorption of the light or transmission of the light through the object, because liquid is quite uniform. So the comes out on the side really would not have a pattern. So you can say that you can try by imaging only that. So for example, if you were doing if there is a change in the color and you are doing the process and there is a change in the color. Right now we do that by human eye. Now you make a decision that when it turned the color, and you make a decision. Now depending on the day, you might one day maybe making a decision when the color is changing by a few gray levels. Other day maybe making that is more than that. You will detect. Somebody else will detect differently. You can use a camera there, color camera, which you can say that the gray level changes from whatever the initial level is by 5 gray levels constant. Then you type in this company example, or your color change happens. You can use imaging for that purpose, but you couldn't use for classification because you will not be able to say that if the color changed 2D.
For example, I'm taking an example of oils. In that case, if I'm taking oils from different sources, so might be there is a difference in the viscosity. So just by looking at the image, we can tell that there is a differentiation of the oils. Is there any pattern of arrangement of molecules, triglycerides in the oil samples? Is it possible?
I would say So first thing is like, so your oil would have to be in a petri dish when you're taking
yes,
the image.
Yes, and petri dish.
Yeah, in a petri dish. So when you take the image, you have basically do a calibration or correlation whether if you change the color, does that color relate to, for example, green content in the seeds? So you would correct that as an example. So you might say, for example, that you have a canola seeds or rapeseed, and that has green seeds in them. So when it has green seeds, the color of oil is darker, as an example. And you might create oil samples having a 0 green kernels, 2% green kernels, 5% green kernels, 10% green kernels, and then you take the images using the camera, and you might be able to say is that this green, so your mean value of the, in that case, green color, or mean value of your RGB colors relate, is the relationship is linear or is it curvilinear? So from that relationship, now you can use just the image and then you can say this oil came from seeds which had 5% green seeds.
But that is like, first we have to
do the calibration
of the lower to higher, and then we can tell.
Then you develop that correlation and you can use that, and that becomes your tool to do the decision making.
It's similar with powdered particles.
Same thing with powdered particles. As long as you do the calibration, you can do the powdered particle like wheat flour. You might want to figure out how much of the brown layer is part of the wheat flour. So you produce the samples with different brown amounts, and then by taking the image, so that you do basically the calibration, and once you've done the calibration, the new sample comes, you basically take the image and say this one has this % brown, or brown layer embedded in it.
I think for oil it is not possible because there is not much difference in the oils in color, in terms of color. You may find some difference in viscosity, but the color will not.
Yeah, the color would be only different is that especially if the green kernels keep increasing. So like if you take, for example, rapeseed or canola seeds, and it has 10% green kernels in them, and 90% are mature, you would have a dark.
Chlorophyll or some
chlorophyll, yeah, chlorophyll.
Not refined oils. We are
Oh no, the refined oil would not have. No.
because we remove all these.
Yes,
Yeah, they get all removed. Not in the refined oil, in the raw oil.
Yes.
Crude oil you would have that.
But there could be a very good application. I don't know if I've heard, for example, this brand content, brand specs has a very positive over the ash content.
Yeah.
Ash content is used as a quality attribute for your flour. Higher the ash, more the brand, and poorer is the quality, or you might get more extraction from the flour. So, but it could be very good, the method, if we place a retardation ash, because it's quite hours to do the incineration, right? So it could be a very good method if we can develop, okay, if this much is the brand, because brand has a direct relationship ash. So this will be the ash content and this will be the method.
Yeah, and that certainly can be done. I don't know if anybody has done.
I don't know what accuracy it will measure, because usually we say if the ash content is less than more than 0.4%, then we say the flour will break poor. Good quality. This is not pure. So it means more brand has been done. So if it can determine at level 0.4, 0.5% ash content, then this will be very good.
I think that certainly a lot of people have looked at the quality of the wheat flour using the image processing. Because I don't work directly in that area, so I'm not sure of what level, like what accuracy they can detect. But it certainly can be done. And the testing can be done for any flour, not the wheat flour, any flour.
Yeah, and this is for great, because when we do the exterior cooking, right, we require particular size of butters. And we don't want that the white specks, particularly in corn milling, we get a white speck, that stick cap portion of the grain, right? If that enters in that, and the quality of the extruded is not good. One is that because in extrusion cooking we use very low quantity of water. And when the fine particles are there, they quickly absorb all the water which we are using. Very limited amount of water we are adding. So when we do the extrusion cooking of such flours, so the fine particles they get gelatinized because they were having water. The coarse particles they remain ungelatinized. The extruded snacks they are of poor quality. So I was working with one of the corn milling industry. They were asking me that we want to clearly know whether this 5 watt or this 40 code is there. But we were doing with the help of thieves.
To me, I mean, I have not done work in that area myself. My feeling is doable.
Like Canadian Grant Commission has counted like they grant, like they count using the
I can arrange the grid samples, right, for you. You have built all this system for image analysis materials.
The spec counter Canadian Grant Commission using spec counter.
What is the cost of that?
I'm not sure with that process. When I went to the city, I saw a spec counter they are using. Even like Canadian definition based. It's just like took an image of I think 50 tons of sample, and they will just like once they build the sample, they will put it in. Then they will analyze how many wrong specs in there, and then it will count and say like it's 300 specs in there or like 400 specs in there. So it will count and say along with the ash content. But for standard, they are using ash content for grind grading. But for the milling quality performance, they use this spec count.
Okay, can we wear the black, the sports on chapati?
Yeah.
Oh,
that is the simplest problem.
Yeah, because we are doing, one of my students is wearing the chapati quality. And we are not having the data for that. Yeah. We want to see how many specs are there, whether the quality is good, but we want to link the quality of this type of sugars, what type of fat is there, what is the chemical reaction that are occurring. Because they are responsible for this, these small sports. Yeah. So we will be interested in that. Maybe if my students can try how to measure the specs.
No, that would be very easy system to design.
Yeah, only thing we have to standardize.
Standardize the raw material. So like if this chapati came with this amount of you have to know what comes.
Yes, that we have all the data.
So once you know what this chapati came from, then the features you extract from that chapati, and then you would have to probably prepare 80 or 100 chapati with the same flour content, so that you are when you are doing the training, network is being trained with that many samples. Then when you present the new chapati, it should be able to tell it came from what kind of flour.
Yes.
That's certainly doable. But I don't think, I have not come across anybody working on chapati. Maybe.
No, I have
not come across this.
This one, the chapter of the book chapter on the indigenous textural properties of indigenous. Last week I completed that chapter, and in that, I have given all the data. That's why I'm asking. So what type of, because we have done a lot of work on the molecular weight proteins and how they are linked to the quality of the soil. But I was reading that people have measured with the hand, like these number of specs are like this.
That's something and that would be good, I would say, probably in the master's thesis. Okay? Any other questions?
HSA calculations.
Yeah. No, it would be. Yeah.
That RGB values used, is that RGB 0 to 55 values of a single pixel or the whole image? For calculation of theta,
No, it would be, so in this particular case, so if you had RGB values, so you would be taking the mean, because HSI, so R, G and D here is the mean, R value, mean G value, so it is the mean values.
Mean values of the
whole image, yeah. So because then you get HSI for the whole image, but you want to, for example, another way you can, so it would depend on the application. So if you were looking at the, only the center part of the image, rather than looking at the whole image, then you might say I'm taking 100 by 100 pixel by 100 pixel area of the image, and I'm converting that into HSI because I'm going to make decisions based on that. Okay.
Is that we can make a whole image into patches of 4x4 or 8x8?
You can make many patches, and then so another thing you might do is like if you did that, so that would be called the subsectioning analysis. and you can use that, can become one of the features then, which basically would end up representing almost like texture, because your mean values would be different in different parts. So if you took the full image and make it into many smaller corners, like maybe looking at graph paper, and if you had a different mean of any color or HSI, this corner and different mean this corner or different points along the edge, that in itself can become a feature. Okay.
Is that HSI value can calculate for each pixel also, or it can be calculated for the whole image?
Or you can calculate for each pixel also, because it's based on then in that case R would be the pixel R or pixel G and pixel B.
In case of calculating for each pixel, in calculation of S, what's the minimum R? What is the minimum in RGB?
No, so each pixel would have its value of R, value of blue and green. So let's say R for a pixel number 1, R was 100 and G was 110 and B was 120, then you would take 100 because that's the minimum of R, G or B.
But the HSI, all values are fully dependent on RGB values. HSI are fully dependent on RGB.
Yeah.
Then if you are going for RGB color analysis, that HSI color analysis, why do you want to go for HSI analysis?
I think it's more the HSI is I think what's different, because when visualize as you mean, we are looking at the hue of color and versus more close to the human perception. So that's why HSI people, like a lot of people who deal with the color, feel that HSI is better representation of the color than the RGB, because everybody visualizes RGB. So that's the only reason you would convert RGB to HSI, and then people can